So another version of this problem you can find over here, you'll see it. It is the flux. I'm just going to find it real quick here. Not here, rather this one. So I just want to show you a variation of this where you go, yeah, I have a point charge and, you know, I want to find the flux through this plane over here that is a distance L away from me. Now, this is doable using integration, but it's very, very cumbersome. You can see that the electric field, again, as it hits the plane at different points of the plane, it will depict various angles of incidence. And to find the relationship between theta, x, y, it's just very complicated. So instead, you think of this in a different light and you go, what if I try to put this inside some symmetric surface and in a symmetric position as well? I will always know that the total flux through that closed surface will be Q over epsilon naught. And then I can make this a building block of my closed surface. So you go, okay, if I am L away from this plane, right, and the plane itself has dimensions L, then maybe I can construct a nice little box around my charge, right? And each side here of the box will have 4 of these planes, right? And each side of the box, again, we have 6 sides on the box that we're going to put the charge in, and then four planes on each side of this kind. If you do that, you construct basically this contraption here. And the benefit is that you can see here's like what you're trying to find the flux through. And you have some surface that you know the flux through already. From this white box, the flux right now, since the charge is sitting in the middle, is again Q over epsilon naught. It doesn't matter where I would put it inside the box, but why I have it in the middle of this box is because I want each side to receive equal amounts of flux. And obviously, if I'm in the middle and my field is R dependent, this side, that side, all of these sides will be getting the same number of flux, the same amount. How much? It would be the total divided by the number of sides, right? So Q over 6 epsilon naught in this case. However, I see here that the plane I want to find the flux through is 1/4 of a side. So if it's 1/4 of a side and a side receives Q over 6 epsilon naught, you can see I just need to divide the Q over 6 epsilon naught by 4. And if I do that, I get Q over 24 epsilon naught. That's my answer. So think of it again. If you ever see this problem, think again, what closed surface can you place the Q in symmetrically and in a way where this is a building block to the surface that you just closed the Q in. You see, this is a building block to the box that we closed the Q in. And that's how I arrived to the Q over 24 epsilon naught. Okay, very simple problem once you've seen it, I believe, once, right? Now, in our case, so I wanted to show you this, right, as an aside. Because who knows, maybe it was on your review, I don't remember, or it might be on your midterm. Now, equivalently here, you have this Q, and you're trying to find the flux through this disk. It's a disk. It's like a circular type of region over here. And you go, okay, I mean, I've kind of already spoiled here what the closed surface should be and where Q should be positioned. I think you can see it. It's a cone, right? The closed surface is a cone. And the correct position for Q to be here would be the tip. Now you might say, why not in the middle, George? Well, because again, we're not focusing so much, I would say here, on the sides of the cone, what the flux they are receiving. Like we're not focusing on the curly part. I'm focusing on the bottom, right? And if I put it here, I'm not a distance L away from the circle as they require in the problem. So I need to keep my distance from that circle and be at L away from that circle. So from here, once you have this idea set up, it's starting to look up like you have a plan now. Notice that, okay, we can set this as an integral now. I want to get you the flux immediately. That's what I need to show you. And then we'll talk about some other things that pop up. So what's going on? Okay, let's say right now, again, you're trying to find the flux through this disk. Oh, how do I do it? Well, I remember, again, that my electric field from a point charge is R dependent, okay? And if you remember the formula for it, the electric field from a point charge is KQ over R squared, right? That's what it is. So, and it's also in the radial direction. Okay, that's cool. So again, if I draw the electric field lines of this charge Q right now, one of them would be like this, another one could be like this, right? I'm just drawing a few to show you what the heck is going on, right? And you see how they crisscross, how they cross the disk at various locations, right? So I'm thinking to myself, there has to be something I can do here to calculate the integral of E dot dA. That's what I need to do to get the flux. So I need to calculate this integral. I have the electric field, but I don't exactly have dA right now set up for myself. So you go, okay, let's think about this for a second, okay? I'm gonna delete some of the structure. I don't need right now any of this stuff. I just need the disk that I'm trying to find the flux through. I'm gonna make it a little wider so that it can put some structure in. Now pay close attention because this is, again, this is very notorious. Okay, I wanna think right now how I can build a building block to calculate the flux. When I'm thinking of building blocks in general, right? And when I do like my electric field or when I do my whatever quantity I want to integrate, I'm thinking something that experiences the same amount of the quantity I'm integrating. That's a mouthful, but it means, again, I'm looking for a building block that will have a constant electric field through it right now. And I mean, not only direction, but also the value of the electric field is going to be the same. So pay close attention here, how I can build the building block without even knowing what it will look like. If I put an electric field line right now from Q, just the radial electric field line, it goes like this, okay? And I repeat the same thing to the bottom. I see there's some kind of symmetry here. So I put it there and then I flip it, right? I want to rotate it. It's not going to let me, is it? It's not going to let me. Okay, so I'll do it by eye. I don't know why it's not letting me, but I'll do it by eye. Notice again, the point again where they cross the disk there. You go, that distance right now, right? That distance from Q to this X, isn't it the same right now as if I was to go the bottom way? Like if I was to connect here the Q to this X, this is the same R value, right? So I'm noting that these are exactly the same right now. These are R's that are exactly the same. And I'm thinking to myself right now, here, I have to have something around here that I can show you. One sec to do a demo. I wanted a CD, like a perfect disk, but the best I've got right now in terms of a disk is literally something random like this. Okay, so here's the disk I want to find the flux through, right? And imagine again, I want to make sure you can see it in your perspective. So here's the disk, okay? If I turn it sideways, I'll keep it a little bit like, so you can see the disk over here. Notice again that, again, what I've drawn on your image is like an electric field line hitting here and an electric field line hitting here. But really, everybody else around here shares the same distance from the point charge. Like I can draw a circle right now of positions. And again, I'll keep the tip here fixed to show you this. Like where I'm pinching right now, the pen is the position of Q where I'm pinching it. So keep an eye here. I could draw, look at the tip of my pen. I could draw around here. I could draw around here a circle, and every single point right now of this circle will be the same distance from the point Q right now. Every single point on that circle. What am I suggesting? I'm suggesting this. Connect these 2 points with a little circle. And every point, again, in this circle, right, will be an equivalent distance R from my Q. Every single point right now. It's hard to see on this diagram because it's a false 3D diagram, right? You're not going to see the depth, but I want you to imagine again, every single of these orange lines right now hits that circle. It's the same distance away from Q. All of these points right now are the same distance away. Okay, so why am I caring about that? Well, you know why? Because this guy right now depends on the value of curly R, right? So again, how to pick, again, building block. Okay, I need, okay, a surface, or again, some target. I need a surface that experiences the same strength, strength plus direction of E field. Okay, this is how I'm thinking about it. I'm setting myself up. In this case, okay, in this case, a ring on our disk is always a distance. Okay, I have to be careful. In this case, a ring on our disk has all its points an equal distance R from Q. And since E is a function of curly R, all points on ring experience the same strength of E field. See, that's what I'm saying. Experience the same E strength. That's the idea. So that's how I go about thinking, right? If you ever wonder what goes through my mind, that's what I'm thinking. And that's how I picked to do the ring here. So let me explain then, how do I proceed from here, okay? Now that I know that it's going to be a ring, how do I proceed further, okay, to calculate the flux? You might be tasked with this problem, so it's good to know. So in the next diagram, I'm going to show you now how I'm going to calculate the integral for that flux. I don't need all these electric field lines. Now, one thing I want to show you, though, is that the normal right now of the plane, okay, the normal of this disk, I want you to see that the angle between the electric field and this normal is always preserved. You can't see it well for the in-between values, but you probably can tell that we will be able to find out what this angle theta is going to be. It's going to be something that we have to work out, unfortunately. So you see again the normal of the plane. Sometimes it will be completely parallel to the electric field. Sometimes it will not, which sucks, right? But we will be able to do something about that in this problem. Remember, this was illegal to do when we were trying to find the electric field using Gauss's law, right? I had to have these always parallel to the electric field. But now I know what the electric field is, right? So the only unknown is that theta, really, that is between my electric field line, right? And my normal. That's it, really. So yeah, it's not the same situation. I already have the electric field here. I'm just trying to calculate the flux. So in the next diagram here, I want to show you how we continue it then. Now that I know. So we know that it's going to be a ring, okay? And then what do I want to do next? Widen it a little bit, because you see, I gotta, remember with any building block, if you want to span this, you gotta smear it out, right? You gotta smear the building block to cover the entire object that you're trying to analyze. So what am I suggesting then? I'm suggesting that you gotta smear this guy to become an annulus, essentially. That's what's going on, okay? He's gonna become an annulus. He looks like a galaxy right now, the whole thing, it's funny, but that's what you have to do. And again, you're gonna ask yourself, what is the surface area of this piece right here? Gotta figure this out, okay? And how much flux is this getting? This pink ring, okay, so the pink ring, annulus rather, annulus will receive equal, I have to be careful here. The pink annulus will receive some d phi, okay? And then we're gonna have to smear it out to find the entire flux through the ring. Okay, we understand the goal here. So you're like, okay, what do I do next now that I know this stuff? Well, we gotta keep setting this up. What is dA here? We gotta find dA for this ring, okay? That's what's going on. And I can start thinking about this for a second. So this ring, okay, the whole disk has some radius. Okay, we will be given this, but where am I here? Let's see. This ring, this annulus rather, keep calling it a ring. It's an annulus now. It's really, really, really thin, okay? It's not as thick as I've portrayed it here. It's really thin. And I want to emphasize that because the inside and outside radii here are considered essentially the same. Just like when you were doing the rubber band method, inside and outside, again, upper and lower radii were considered to be the same. Because again, you have this being like your R right now, the big guy here, and then this is just a tiny dr, right? So you get what I'm saying? Like it's the outer radius is really just the inner radius when you take the limit as dr goes to 0. So you go, okay, if now I come and snip this ring over here, I get a rectangle, okay? And the sides, we've seen this before, the sides, you got 2 pi r for the long one, and then you can see the short one is just gonna be dr, okay? The short one. So, okay, I could get right now the surface area of this. You can see how by multiplying these two things together. Okay, that's what's up. So you go, okay, that's fair enough. Now, what about the electric field, right? We got to find how the electric field interacts with this. And this is not yet the vector. This is not yet the vector of dA. Well, where does the dA here point? Let's think about this. All the normals on that pink guy point right now toward either the negative x-axis or the positive x-axis. So, you know, I could slap a direction on this, okay? Just gonna put it over here, just showing you some of these normals. They're all pointing in this direction right now for this ring. Okay, so I would say, if I wanted the full vector, that this dA is pointing toward the X direction. Okay, and then I would like to find how the dA interacts with my electric field. So let's see what's up. The electric field's coming in here. Obviously, it's pointing in the R direction, right? In the spherical R direction. So we have a hybrid here of Cartesians and sphericals. We'll have to think about how these things interact. But that's what's up, right? This here is my E field, right? And again, if I have a normal vector up there, you can see that they make an angle with respect to each other. I'm going to draw the electric field just here right now. Okay, just like that. You see again, the normal and the electric field, like I said before, they make an angle with each other. Okay, good enough. That guy over here, again, is, well, the normal of the surface, which we established to be x hat. So let me ask you something. What component of the electric field do you believe contributes to flux here? Because we have two components. If you use this normal, we have two components to the electric field. You got this one right here that I'm drawing, right? You got this one right there. And I want to know, which one does Kelly believe will contribute here to the flux? What do you think?
EX.
EX. How can I get EX in terms of E though? I wanna ask, yeah, if you want, Kelly, go for it.
E cosine theta.
E cosine theta, okay. That's actually inside the integral too, right? Like if we were to do the flux integral, okay, it says E dot dA, okay? And when we do the dot product here, what we get is E dA cos theta. So that E cos theta is already built in the flux integral. I'm just reminding you where these things come from. Like, you're telling me right now, that's the only thing that's going to contribute flux. And then I just need to integrate it with respect to dA. And I'm done. That's the only thing that causes flux. So in my next step, what I'm going to do is I'm going to introduce what E is in terms of R normally. So I have, again, KQ over the spherical R. That is the spherical R. Let me show you here what I'm talking about. This guy here is the spherical R. You can think about having spherical coordinates right now, like this, I guess. This would be the center of your spherical coordinates, right? And this is like your R, right? That measures again distance from the origin. So that's what I mean. This can be called R right now, just the spherical R. So, okay, we don't need to use curly R anymore. We know this is the spherical R. Okay, and the dA right now, you said, should be 2 pi r dr. 2 pi r dr. But I have that darn cos theta that will not leave me alone right now. How do I deal with that? And here's where the cool thing happens. So you go, okay, can I get something about cos theta? I really don't like this guy. What is cos theta really? Well, if I extend this line backwards over here, okay, do you see what's going on? Like I got theta to be this guy right there, right now, because these are opposites. Right? This is a right angle triangle right now. You see that? And you know what? Hold on. I'm changing my mind a little bit on who to call theta. Okay, I'm changing my mind just a little bit. And you should too, because girls, if I have a spherical coordinate system here, okay? If I have a spherical coordinate system, I'm just gonna grind your brain a little bit. Look at this. Look at this 1 second. If I put a sphere here, okay? ignore everybody else. If I just put a sphere right there. I don't know about you. If this was my z-axis, I'm just bringing it to your perspective, like what you're used to seeing. And this is like the y-x plane, let's say. That will change the names of the electric fields. That's okay. So that would be EZ here. And that would be some kind of planar component, EXY. But we don't care about that, we said. Take a look at the sphere. I don't know about you, but this, or actually, yeah, the angle with respect to Z, remember the Z axis here? That is your polar angle. Hold on a second, this guy's your polar angle, right? Like, this is the guy again that you vary, watch me. This is the guy that you vary from 0 to pi over here to span that sphere. Remember? He starts from here, from the North Pole, and he gets varied all the way back to pi to span the sphere. So secretly, this is your running variable theta in spherical coordinates. So I'd rather use that theta right now, okay? And I'm being very, very careful here. I don't need this part anymore, okay? I'm glad I'm making these little mistakes. They're not mistakes, but they're just like going down the wrong path and then realizing, stop, you know, this is not going to get me far. I like when you see those too, when my solutions. So I stopped because I was like, George, this electric field and this line are parallel. And theta is the angle between this line and a horizontal line. So that should be the angle between this line and the horizontal line here. There it is. And then I realized, my next realization was that this is actually the polar angle in spherical coordinates. I told you why. Fit the sphere here and I showed you, right? And if you still don't believe me, I did this yesterday, can do it again. If you still don't believe me, there it is again, with respect to the z-axis, right? It literally is the polar angle. So what I can do here now that I have the cosine theta, I can figure out where theta will vary from and to, and do this as a double integral, okay? If I want to, I can figure out what, again, is going to be R's dependency on theta and do this in the theta world, or I can do it in the R world. I have to decide. I have to make some decisions here. But the important bit is over right now. I know what this guy is. He is accidentally, didn't have to be this way, he is the polar angle. Now, my recommendation is that you do this in the R world, okay? My recommendation. You could choose not to, okay? I've told you there's more than one approaches in these problems. So if you do it in the R world, I got to get rid of the theta. I can't keep it because theta is dependent on R. Let me explain. You see here, again, this is the spherical R. I have to be careful. And this is the R here. This is the cylindrical R. We have to distinguish these two. 1 second. We got to do a good job of distinguishing these two. The cylindrical R, sometimes they're calling it rho. I've seen it as curly R. I don't know. I'm going to pick something. I'm going to pick Y. How about that? Let's pick Y for that. That's Y. No pun intended. I'm just going to pick Y for that radius. Whoops. And then, of course, that guy up here is going to be dy. It's okay. We're just changing a few names to make sense of the problem. And then that means here, this is 2 pi y dy. And then we have this guy here for our area element. That's cool. Okay. So our integral is in terms of y when we put it all together. Okay. 2 pi y dy. So you go, okay, does theta depend on y? Can I ask Olivia what she believes? So if I change the value of y, Olivia, make it this big right now, okay? Tell me if your theta is changing. Watch what's happening on the diagram.
Yeah, it's increasing.
So we can't integrate yet, okay? I can't go and integrate yet. I'm not going to get anything meaningful because this is a function of y. Okay? This theta here is a function of y. So let's go and figure what it actually is. I think you can probably tell. They've given you how far away you're standing from this this disk, by the way. I gave it to you as L, capital L, and I'm seriously hinting right now what you should do next. Okay, so that's L. That is a very big 90 degrees right here. Okay, what would cosine of theta be here? I would assign that to Grace for a second. Let's let Grace have a word.
L over R.
L over R. Beautiful. So now that we have that, right? I'll put it maybe over here, I guess. Now that we have that, we're ready to roll, okay? Because I know what R is going to be. I can figure out R really quickly here. Who wants to take a jab? R in terms of Y? What is R in terms of Y? I want, actually, let me ask Aaliyah. So I want everybody to speak. R in terms of Y, and Y is right here. What do you think, Leah? If you can hear me?
R is equal to y, y over sine theta.
I'm not going to want to go back to the theta world. I want to get away from that. So I probably want to use Pythagoras. So what's R going to be here?
Y squared plus L squared, like all under square root.
Beautiful. All right, so we got that. Putting it in here, okay? And this is pretty much, I would say, the end of your physics part. Like once you have these things in shape, okay? I guess you can include the flux, right, in your physics part, right? But that's the end of your physics part, and now you are solving. So let's get it all going. So I have all of this. I guess I'll put it upstairs here and then do the integral, try to figure it out. So KQ is a constant, right? It just sits outside. So does the 2 pi. So 2 pi KQ. All right. And then inside right now, I've got a few things going on. So I got y dy over, I'm not going to replace the r yet because this guy's coming in, the cosine theta, which you said is L over R, right? So we got a little bit of a change here. So the L will come outside. We got 2 pi L KQ, and then the integral of y over R cubed, but you told me what R is going to be. It's going to be y squared plus L squared, or I'm going to write it like this because I'm about to do something again. So this is, again, square rooted and then cubed. So 3/2 power. That's your integral right now. Can anybody enlighten me? Can Natalie actually enlighten me on what the bounds are, since you can type those easily? What should the bounds be to span the entire ring right now if it has a radius capital R? I don't know if we can see this line here. That's capital R. She's saying 0 to R very correctly. Whoops. All right. We got it. So again, that's what I'm doing, 0 to R for this integral. Now, you can use a cheat sheet. We usually have these in physics on a cheat sheet, but if you have to solve it, it's a trig sub. How I will do it is I will basically say over here, I will factor this outside. So it's going to get square rooted and then cubed. So it's going to become L cubed on the denominator. Going to have it like this. Y dy over 1 plus y over L squared to the 3/2. I think I did an integral like this yesterday. but again, this is how we go about solving it. 2 pi LKQ. So some of the L's here cancel, get this to cancel. And then your U sub, or rather your trig sub, excuse me. You base it off of the Pythagorean identity here for sine and cosine. Okay, and you divide both sides by cosine to give you tangent squared plus 1 is equal to secant squared. That's what happens if you divide both sides by cosine squared. You use this because it matches the form here, remember? So you let y over L be equal to tangent of theta. And then, of course, you can get what the relationship is between the derivatives. So if you take the derivative with respect to theta on the other side, that's secant squared. And that means you can replace very easily here what dy is in terms of d theta. Beautiful stuff. So you go in and change this. Yep, we're good. And that's about it. That's about as much as we do right now. We continue. We get 2 pi KQ over L squared. The bounds are, I'm not changing them right now. And I'm going to have here y dy. Y is L tan theta. dy is L secant squared theta d theta. Denominator is 1 plus here tangent squared theta, and then 3/2. Now, this guy, we know from this identity that he's going to be secant squared. And then we realize what's going on. It's a little hectic, but it's okay. Look at the L's go away, by the way, before I do my next step. So I only have left 2 pi KQ, okay? And then I'm integrating right now. What has remained? We have a tangent theta, a secant squared, a d theta, and on the denominator, this secant squared is getting square rooted and then cubed. So you have a secant cubed remaining. Okay, looking all right. So, when these cancel, what you remain overall is 1 over secant or just cosine, right? That's what 1 over secant is. So you might think that it's still pretty complicated to solve this integral, but you'd be wrong. Because tangent is sine theta over cosine theta. And these guys right now, remember, they're just amounting up to a cosine theta. The reds here, I'm going to highlight them because you're probably going to get confused. So these guys, when they canceled right now, they literally amount to cos theta. That's what I'm highlighting here. And this is the tangent. Okay, so you don't get confused. I hope that makes sense. So you realize again that this goes away. You realize that goes away. And what are you left with? It's just a sine function. Whoa. Okay. That's convenient. Leah, integral of sine? Where did it come from?
Negative cos theta.
Negative cos. All right. So we put the bounds back, okay, slowly. We don't have to rush here. 1 second. We need a cosine. You said here that tangent is this. So make up your little triangle. You said that opposite is y, adjacent is L. Obviously, the hypotenuse is y squared plus L squared. So if someone asks you for cosine, you will tell them adjacent over hypotenuse. Remember, this is how we do trig subs. All right, fine. Let me put that back then. And now we can return, like after this, we can return to the normal bounds and evaluate them, right? That's the whole deal. So we have the 2 pi KQ not changing. Okay. And we have this getting evaluated, Natalie told us, from 0 to r. So let's see what we get. Okay, so 2 pi kq, and then we open up a bracket here. We got L over r squared plus L squared minus L over, again, you can see here, not r squared, 0 squared, or basically just L squared. Perfect. Ah, I forgot the negative. I almost did it again. I forgot the negative, right? Okay. So if you keep the negative outside, we're gonna have to distribute it eventually. But you can see what we get. We get 2 pi kq. All right. And then we go over here, and inside we have, let's write it like this, 1 minus this guy. Now, you'll notice that this doesn't look like our answer. Okay, you'll be like, wrong. Not quite. I'll explain. This is actually correct, okay? So compared to the answer, I will be, again, very impressed if you tell me why the answer looks like this and our answer looks like this. And I will start helping you out, okay? I'll do my best to help you out, but tell me if you see it. And the theta here is the opening angle. We can consider it to be a constant. Like, that's not a running variable. That's literally your opening angle there. So tell me if you see it as I'm doing this. What do you think? Whoa, I forgot something. Excuse me. This K here, get rid of it, okay? If you want to match the solution, right? So this K here, get rid of it at some point, maybe here. So in the next bit, make sure you write this as 1 over 4 pi epsilon naught, right? Otherwise, you're not going to get matching answers. That's what it is right now. Unless you have a dielectric, that's what it is. So what's going on? We got, again, 2 pi times q over 4 pi epsilon naught. And you can see that these go away and almost go away. And you've got here q, hold on, q over 2 epsilon naught times this stuff. There we go. Okay. Now you're good. Sorry, I didn't want you to get confused with the K, right? But I should have started the electric field like up here with 1 over 4 pi epsilon. That's on me. You know, that's on me. Okay, so what do you think? Did anybody come up with what's going on here? Why are they different?
Cosine theta is changed to the coordinate.
Can you see that this side here is r squared plus L squared, and that cosine of theta naught is literally L over this. Can you see it now? Can everybody follow what's going on here? This cosine is adjacent over hypotenuse there. And that's exactly what we have here. You see it now? So
I'm confused. Where did the negative go?
Which one of the negatives?
Like, you take out the negative from stepping in the...
Yeah, I've already done it over here, right? So I had the negative here. This was my 1. This was the cosine term. So I flipped them. The negative was here, right, at this step. So that's 1. Okay, that's my 1. So then I distribute it and I flip the order of the terms inside the bracket.
Oh, okay. Thank you.
Don't worry, I'm not cheating you. I always take care of my negatives. So again, if the only difference is this is written in the linear variables, this is written in the angular variables. So if they gave you an opening angle here, that would be your answer. If they gave you the distance and the radius of that disk, that would have to be your answer, because you're not working with a theta naught. They're not giving you this, right? So that's the only difference. Sometimes you got to switch the angular to the linear version. You'll see that actually happening quite a few times. So I hope this makes sense. Okay, the difficult part was to pick the building block, but I explained my logic. I was looking for something that experiences the same electric field throughout it, right? That's my building block. And once I had it over here, I went ahead and let me delete that so you can see this better. I went ahead and build the situation, okay? I smeared the building block because I want to cover the disk, right? But I smeared it ever so slightly that the electric field strength is not different on the inner radius versus the outer, because they're differing by a very small dy. So the electric field that hits this side, this circumference, is still the same as the one that hits the inner one. It's an approximation because dy tends to 0, right? We smeared it ever so slightly. And this is our actual building block. So you smear it to form the disk. If I could find what the flux is through this annulus, I can then integrate it to find the flux through the disk. And that's exactly what I did. So I found the dA of this guy. I found the electric field that he receives, took the dot product between E dot dA, and then integrated. That's what you see me doing. So I determined my dA first for my little annulus. And then when I need to do this integral to find the electric field throughout the disk, this being again the annulus over here. The integral was a little bit rough, okay, around the edges, but once you simplify it, it's just a sign. Okay. And then we worked out what the answer needs to be. Questions? What do you think? If there's anything that I didn't go through well, just let me know. Yay, nay? Olivia?
It's okay. I'm having a bit of a rough time following because I don't remember flux too well, but I'm just kind of going through it step by step here.
Okay. These are on the complicated side, these problems, right? They're not easy to think about. Okay. But my job is, again, to grind you, right? That's why you're here. It's called the grinder. So you will notice that the next problem has the exact same solution. Okay. But the way you get to the solution on this one is more elaborate. So let me explain. You have a charge Q on the next one, and it's placed in the middle here of a sphere. But you go, I don't want to find the flux through the entire sphere. I want to find it through a portion of that sphere, right? That's it, a portion. So through a cap right now on that sphere. And we go, okay, if that's the case, let's think a little bit about how we can approach this. You need, again, a building block. And George said, what better building block than one that has a uniform electric field throughout it? I don't know if you can see it in this case, but Q being here in the middle, if I was to aim right now, like let me put a line to show you something. If I was to go over here, let's say this is, again, we're on the surface, so this is a constant radius here, okay? Constant radius R. But look at me right now. I'm sitting at an angle, some opening angle theta. If I move around, look at this. If I move around like this, Okay, if I move around, my distance from the origin is still capital R. I'm just drawing a circle right now on the surface of the sphere. That's what's happening. I'm drawing a circle on the surface of the sphere. Maybe some of you are seeing it already. So this pink line, even though it's changing size right now on our view, it's not in the real problem because we're lacking the depth information here, right? We're lacking the depth. This is always capital R right now, always, this pink line. And it spans this ring. Interesting. So this guy right there spans a ring. Again, this is our capital R. Maybe I'll delete this one and keep that orange line. Again, you can see, let me explain. What you're given is the opening angle of the polar cap. You're given like the edge over here, the angle like that, okay? Like this line here connects you there. You're given the angle that this edge makes with your z-axis. I'm going to draw it on the other side just to save some space here for our drawing because it's going to be symmetric. That is the opening angle of your polar cap, and it's the same on the other side, right? And that has length R again. So does this. I know they don't look the same, but again, you're having a false 3D diagram here. So you look at this and you go, okay, this experiences the same electric field throughout. That's good. What has George told me to do? He said smear. Smear where? Smear in the direction you want to integrate, right? The flux. This is literally the rubber band method right now, by the way. You can see it. I don't know if you can see it. This is a rubber band. All of a sudden, this ring, when you stretch it, when you try to stretch it over the sphere, it becomes a rubber band. Now, this is a huge rubber band. In reality, again, these things are right beside each other. They're like this, okay? You can't see them. They appear like one. The difference, again, between the top and the bottom part here is insignificant. But I'm drawing it this big so we can put our stuff in there, right? Obviously, this side here, we've seen it before, this ds, okay? We've seen it before. Can anybody help me obtain ds? Can Kelly help me get ds right now? Do you remember what it is, Kelly?
He said
Kind of helping you there.
phi,
What was that?
RD phi.
RD theta. RD theta. Okay.
Yeah.
All right. And now, okay, this is our start. And I want to find, again, the area inside this rubber band, right? That's what I'm trying to do right now. So if I snip it again, this rubber band has a certain radius. This is the cylindrical R again, not the spherical R. So I might, confusingly, your prof might be indicating that as curly R. It is the cylindrical R. I've seen it written as rho in math 227. I don't know how you guys write it. I honestly don't know. I'm just going to say Y again because of this to avoid confusion. It's the cylindrical R though. Okay. The distance from the z-axis is the cylindrical R variable. Okay. So we've got here, this guy's not theta naught, but rather is our running variable theta. Okay. That leads us to the rubber band's position. Okay. And then we can also see that we've got here, if you want, we can draw Z in the diagram as well, right there. Okay, that's our Z. Because it measures, again, this length measures distance in the Z-axis. Okay, we got another right angle triangle. If you can see it right there, that's a 90. So we got a lot of relationships that can pop out right now, but I'll only ask you for the ones that we need. We got to find the flux through that cap, okay? That's my job. So one of the things I need to do right now is write down my integral for this. So the flux through the cap, it's going to be E dot dA. And again, this opens up. E dotted with dA gives you this. What is this angle though? Let's think about this for a second. Okay, we need to think about it for a second. We have a rubber band there. Where is the rubber band aiming? The rubber band is aiming in the R direction. It's normal vectors right now. Let me show you. Hold on. Let me do a demo. Okay. Here's the rubber band around the sphere. Okay. You can see it. And I want you to see that it's normal vectors. They're all pointing in the R direction right now. You see? Like wherever I go and try to take the normal right now on this rubber band, it's going to be in the R direction right now. Okay? I hope it's believable. So we are taking here. I'm gonna have to put things down slowly for you. So first of all, cut the rubber band, make the rectangle that I told you. You know that the long side again is 2 pi y, the circumference of the rubber band, and the short side is ds. And I'm looking for dA. Obviously, it's the product of the two. 2 pi y ds. We'll get to the ds in a second. But again, the direction of the dA is in the r hat direction. Keep that in mind. This is very important. Okay. So you go, what is this thing over here? ds, you said is r d theta. And I know that y and theta are related to one another. Now, if I were you, since I've been given the opening angle of the polar cap, I probably want to work in theta. You know what I mean? It doesn't mean you can't get to the answer if you work with y. But I've been given this and it's kind of hinting me that I should be working with theta, right? So if I see y here, maybe it'd be a good idea to turn it into a theta. I'm just saying. That's how I make my decisions, right? What have I been given from the problem? This is already in terms of theta, so it's good. But then what is y in terms of theta? Grace. What is y in terms of theta? And you can use this as well if you want.
Is it r sine theta?
Yes. Okay. So you use these things, okay? I'm gonna put them here. So you use all three of these things. Let me, 1 second here. I'll take care of everything, don't worry. So we put all of this information together now, all of it, to deduce what dA the vector is gonna be for our ring. So dA is going to be 2 pi r sine theta, r d theta, r hat. And so that is 2 pi r squared sine theta d theta r hat. Beautiful. Okay. Very, very good stuff. So you go, I still have a theta angle here. This theta, though, I got to be careful what this means. This is the angle between E and dA. But you know what? I digress. I don't think you should go in this step yet. Okay? I don't think this is going to be useful. I think this is going to be where you want to go right now. Because I think you can tell me what the electric field is of the point charge right now as a vector. I want Olivia to tell me. As a vector as well. What is the electric field of a point charge? Steal it from the previous.
I'm trying to see what it would be here. I'm not too sure at the moment.
What do you see?
KQ over R squared.
In what direction?
The R hat.
Nice, it's radially outwards. Okay. I probably want to write the K right now, like immediately as like this. I'm just saying, maybe it's a good idea. So again, over 4 pi epsilon naught. Okay, but can I ask you still, Olivia, over here? I'm on the surface of the sphere. Is my R changing?
No, it shouldn't.
Okay. And I should make a note here. Since I'm always on surface of sphere, okay, R is just equal to capital R. Okay. So watch this now. Okay. I will replace that obviously. And I'm ready to roll now that I have this. How come? You'll see. Plug it all in. I don't have to go to this step here. Plug it all in now and see what happens. The physics ends here. It's not a lot, as you can see. I just sat down and think about what I needed. And that's the physics aspect. That's why I highlight it. And it ends here. So next, I plug and chug. I start from my flux integral, and I know what the electric field is. I'm going to bring them in, every single one of these. You got the dA vector, okay? We've been working hard to get this guy. What do you notice about the directions? 1 second. Kelly, maybe?
Is the same direction.
What happens again in the whole process here? This is going to get integrated, obviously, but when I have R dotted with R hat, what ends up happening to those two?
Equals to 1.
Exactly. So I have here the integral. I'm going to cancel all the constants. There's a 1/2 that pops out. There's a Q and there's an epsilon naught. I wonder where I've seen these before. And you have the integral inside. Oh no. What? Again? Right? How did this happen again? And where do you go from and to? Well, again, I want to ask Natalie that question. So Natalie, look at here, my line for theta. We're doing the integral in theta. Where do I want to go from and to? I start from here, and then I end over here. I'm doing a theta bound. Don't worry, Olivia, we're aiming to finish at 9:30, by the way. And Natalie, what do you think about the bounds? So we start over here at the z-axis. Look again what your theta value is going to be there at the North Pole. And I drag it until the angle that they tell me, until the angle that they specify for my polar cap. So what are the bounds for theta? Start here and where they specify the angle again for the polar cap. North Pole sits at 0, not pi over 2, right? So it sits at 0. And then, yes, you go all the way to the angle they specify. So the second one's right. Okay, so you go again from 0 to theta naught. That's the angle they specified, right? Okay, I hope you can see where this is going. So we got again the q over 2 epsilon naught. We got again our negative cosine of theta from the integral. And we're evaluating this in the theta world right now, where we were told by Natalie. But I'm going to absorb the negative sign on the bounds and flip them. Why not? And then go ahead and evaluate rather. So I'm going to have cosine of 0 minus cosine of theta naught. Cosine of 0 is 1. Voila, the same answer as before. Magic. That's again the angle they specify, and that's the flux. Now, if you're adventurous, you can try. So Natalie, if I wanted to find the flux through the entire sphere right now, okay, through the entire sphere, where should I take theta from and to? What do you think? If I wanted to do the entire sphere, where should I take it from and to? Yeah, from 0 to pi. Check. Theta naught equals 2 pi. What do you girls observe? Take a look. Q over 2 epsilon naught. 1 minus cosine of pi. Cosine of pi is negative 1. Your bracket is 2. And it cancels the 2 over here. What do you get? Q over epsilon naught. That's what Gauss's law would have told you. Voila. That's the answer for the entire sphere. Okay, so it works, right? It tells you basically now you have a function that tells you, depending on what chunk of your sphere you want to keep around, how much flux is going through that chunk. And if you keep the entire sphere, obviously the flux is going to be Q over epsilon naught, as Gauss's law says. No weird things there. How are we doing? Questions?
What is flux?
It's the flow of electric field through a surface, right? The amount of electric field that you get through a surface.
Okay.
So it's like, it's a rate. It's a rate, right? Like how much electric field is passing through a given surface. It's like water flow. How much water is passing through a given surface? They have very similar analogies. If you have a field, a field always describes a flow. So it's natural to ask about how much of a quantity makes it through a surface. That's what flux does. Okay. So we're good. We're good with this problem. This is the non-electric field stuff that they're going to ask you. Now we want to start doing some problems where we need to find electric fields, okay? And that's what I'm going to do until 9:30. I'm hopefully going to get to here and finish this one. And then we can come back and hit the other ones. Maybe even further, actually. Maybe we can try a little bit faster. So let's roll. You need to remember again the result for an infinite line. If they ask you to derive it, you need to be on top of things, okay? Every time, here's what I need to tell you. When you're trying to find the electric field now with Gauss's law, you want to know the electric field direction. You cannot apply Gauss's law if you have no idea what the electric field's doing. One of the key things is that you know the direction and the dependency of the electric field. So let's look at the line charge over here. This is infinite, right? It's not finite, like the problem we did yesterday. So if it's infinite right now, okay, it has all these positive charges sitting side by side, and they're emitting electric field against each other. obviously these field lines need to diverge, right? They need to not, you can't have electric field lines cross one another. So when they see each other, they go like this. Okay, what are their options right now? Well, one of their options is to go this way. Another option is to go down, right? Another option is to come out of the page, right? Rise and come out of the page. And another option is to go into the page. You know what that looks like? That looks like, if this is your line, that looks like this. They're going all the way around like spikes. Okay, around your line of charge. They're going all the way around like spikes right now, these electric field lines. So the top view here, okay, the top view, the electric field, I will draw it by hand. The top view looks like this. This is where I have the top view. If you don't understand what it shows you this perspective. Look at the camera. It shows you this perspective of the line, okay? Versus the side view is showing you this perspective of the line charge. So you can see, again, both perspectives at the same time. Now, I go to myself, okay, what kind of dependency should I have right now? Well, like, look at the system that we have at hand. It's a line charge. These charges are literally a 1D distribution. The field is radial, right? It's moving in all directions in the cylindrical R, I should say. So the field here, we conclude that the direction is in the cylindrical R direction. This is the cylindrical R, okay? Okay, cylindrical R, not the spherical. Okay, that's good. What about the strength? Well, again, if you're here, look at this, 0.1 versus 0.2 right now. I want you to understand, okay, that if you're 0.1 right now versus 0.2, you literally see the same picture of the line because it's infinite. Let me explain. This is your line right now, okay? You see that it extends outside the camera right now? So if you're like here right now, if you're here versus here, you see the same thing. The line is infinite in all directions. So when you take a look at the line, right, you still see an infinite line this way and an infinite line that way in 0.2, and the same thing for 0.1. This line extends, right, to infinity, both directions for you. You don't see an edge. You don't see a single difference, okay? You don't see a single difference. It looks exactly the same. Okay, and it's also the same if we raise these points out and inside the page. So you go, okay, what matters then? What matters? Well, the only thing that matters is your translation in this direction, right? So point P1 and P2, I'm going to say the argument here, how we deduce P1 and P2 experience the same picture. But P3, which I'm going to put, let's say, over here, but P3 is closer to the charges. Okay, it's closer to the charges, and we expect its field to be higher, right? So what's the variable then that matters? It's this guy. It's the distance from your wire. And you know what that is called? That is your cylindrical R. That is your cylindrical R, right? So we conclude, okay, we conclude here that the electric field is a function of the cylindrical R. So you put it all together now, your conclusions, one from the direction here of the electric field. You see, I told you, you need to know what the electric field is doing before you attempt Gauss's law. So you conclude that the electric field as a vector, not only does it depend on the value of the cylindrical R, but it also aims in the R direction. So we need, okay, that's how I'm thinking about it. We need a building block, a closed surface rather. Need a closed surface. Need a closed surface of constant R and having normals along R hat. Who is that guy? Who is that guy? Look at what I'm asking. I need a closed surface that has a constant R. Why? So that all the points on it experience the same strength of electric field. And I can pull the electric field outside the integral, basically. But the other thing that I need too is that that surface that I'm using, the surface that I'm using, has normals along the electric field direction. And that allows me to do the breakdown of the dot product. It allows me to do this, right? So I need both of these. What shape satisfies this statement? I think you know. Olivia?
Sphere?
Are you sure? A sphere has a constant cylindrical R?
Oh, well, yeah, I guess just then like the cylinder.
Literally just the cylinder, right? So that's why I have it lurking out here, okay? And then I go, all right, now that I know what the hell's going on, I'll take the line charge over here. I guess I'll make it a little bit better. So the point here is not to teach you the derivation. The point is to explain to you the derivation of the electric field of this, because I'm sure that in your notes you have this, but I wanted to explain why you're doing these things. So the Gaussian surface here, you get to pick again, its radius and its length, okay? So you get to pick this R and you get to pick this L. Whatever you desire. You can call this L, call it L. Okay, now watch this. The cylindrical surface has two caps and a side, okay? So now we're saying we want to solve this equation, right? This is Gauss's law for finding electric field. Okay, so I have satisfied all of the simplifications that I told you to be able to pull this guy outside. But before I do so, notice for a second that this integral can be broken down into the integral of E and then the dA of the cap over here, the caps, plus the integral of E and the dA of the side here. So you see what's up, right? The electric field right now is going this way. Is it ever going through the caps, Kelly? Tell me if we ever get the caps to experience an electric field flux right now from what you see.
No.
No. So that means this integral is 0. We can break, what I'm trying to say is we can break our closed surface into individual open surfaces when we're doing the integral. That's what I've done. I've split this up on the caps and on the side, and I conclude that there's no electric field going through the caps right now, okay? Because the electric field is tangential on the caps. It doesn't cross it, okay? It just grazes it. We don't see something again like this, okay? We see it graze it. So it doesn't actually register a flux. Okay, now that you know that, you understand that why I'm looking again So I can pull the electric field outside. I told you this here, the electric field is always parallel to our normals, right? Of the cylinder on the side of it. So we can always pull outside now completely the electric field like that. Okay. So what is the area of the side? Who's going to take it? Can Grace take it for me? I want the area of the side of the cylinder. What do we know?
Pi r squared h.
That's the
Well,
volume.
no, 2 pi r h.
2 pi r h, and here h is L. Good. That's it. We go on the other side and we ask how much charge are we enclosing? Now this line has a constant linear charge density. We'll put it in here, lambda. I want Kelly here, okay? Kelly, how much charge have we enclosed right now if I've opened the cylinder a length L and the linear charge density is lambda? It's the same old tricks.
Lambda dl.
Not dl,
Oh.
because L, right? Because that's how much we've enclosed right now. We have enclosed L. So it's lambda times L. Good. No integration required for this one. Sometimes you have to integrate, right? If you have an extended thing, and you might have to. Not a big deal. So now you can see what's going on. We got 2 pi r L equal to lambda L over epsilon naught. And then I can finally find my electric field because the L's cancel. Didn't we say that it shouldn't matter on the length of like this direction? Our points here, didn't we say that they're going to see the same thing? It doesn't matter how long you make the cylinder, but it matters how thick you make the cylinder, how much the R value is. And that's what we see here. The L's collapse and you get the dependency that you expected. And of course, the direction, we've already predicted it from the beginning. We walked in knowing the direction. And that's how you conclude it. There you go. Now you understand why the heck we need this logic. You need to know the direction and dependency of the electric field before you even jump into solving what the field is. Okay. Now, I want to grind you a little bit more on this. Suppose someone asked you to find the potential right now, the potential function of this. We're going to do both for each distribution. So I go, okay, all right, if I want the potential, George has told me there's 3 cases. One was when we don't have a symmetric electric field, so I use dV. That's not the case here. The other one was when I can get the electric field from Gauss's law, but I have a finite charge density. And the other one was when I have an infinite charge density. We have an infinite charge density, and that introduced a problem. When we did the potential, I said infinity is not a good place to get as a reference right now. So what do we do? George said, take 2 points, okay? Maybe I'll do it, hold on, maybe I'll do it over here. So the potential we'll discuss over here right now. Take 2 points. Suppose this is like the point of interest, and suppose this is like your reference, right? This is your reference potential right now. So we're going to set the potential here on our potentiometer to 0 when we investigate this guy. You can see that one of them is at a radius r0, and the other one is for free here, like some radius, whatever he wants to be. I'll put him on the Gaussian surface because the Gaussian surface is essentially a probe that measures like the electric field at specific points. So I'll put him exactly on the Gaussian surface. Why not? Okay. So George said, it all amounts to filling up this integral V at your point of interest minus V
at your reference, and we're going to take the integral from our reference to our point P of E dot dl. Okay, so how does this amount to for the line charge? Well, V of P, we want to move this on the other side. So we'll have V of P naught. P is at a radius R. P naught is at a radius R naught right now. Okay? And then we take away the integral, okay, from P naught to P. That means from R naught, if we put in the bounds correctly, to R. The electric field was lambda. Yeah, 2 pi epsilon naught R hat. And we're dotting with dl here. This again will return dr, the cylindrical R. That's why I already knew this was going to happen. That's why I put the bounds first. So all that we need to do now is integrate this function with respect to R. I'm going to put it right there. Of course, you can see that I only have these remaining inside my integral. Okay. I can move the constants outside. Okay, actually I'm going to ask a specific someone. Can Leah integrate this for me? The dr over R here. What is that going to give me, Leah? What function is this? The antiderivative of this? Think.
Ln of
Ln. Okay. So ln. So everything here stays the same, and we evaluate a logarithm between R naught and R. That's going to look like this. I'm just going to do it in one shot. And if you want, you can distribute the negative if you want in the actual logarithm right now and write it like this. Right? It just flips the sign here like that. So that's what you have. That's what you get here. Okay. So George here at this point, when he's here, he's going to ask, can I use R naught equal to 0? Can you? What happens? Tell me, what happens if I use 0 in here as my reference? What do you notice? Olivia?
I can't really remember, but I don't think ln 0 exists.
Yep, it's problematic. So that's a big no-no, because that means if you use this as a reference right now, you have negative infinity as an offset, you're not measuring anything. If you get 5 for your potential, the negative infinity will still make it negative infinity. That's dumb. Okay? So no. Okay, so George will go, maybe it's a special case, and I can still use infinity as my reference. Maybe I can do that. You're being hopeful, but I will crush your dreams here. So what happens here? Grace. What happens in this case?
Wouldn't that become ln of infinity?
We're busted, okay? Okay, it's a bust. And what I mean by a bust is that this guy needs to be some finite value from more than 0 and less than infinity. So again, I'm going to specify here R. This is more advanced than I should be telling you, but R naught needs to be this. So it is a bust, and you have a choice. If you want, set V at that point equal to 0. That is a choice. Okay. Now I know you might not believe me. Probably questionable practices here, but let me show you. We'll go over here real quick and I'll show you electric potential of infinite line charge. Who's gonna tell me? Maybe physics forums. Let's open that one and maybe, oh, another. There we go. Maybe hyperphysics is good too. Okay, so potential, this is a finite line. I should have mentioned, no, I should have mentioned this is infinite. Damn it. I did mention it though. Nice, Google. Okay. Oh, there we go. So what's going on? It's okay, the potential difference increases as you go farther. Here's our lambda over 2 pi epsilon naught. Here's the logarithm of the reference. Not the reference, actually where you want, and the reference on the bottom. And the negative here will flip them around. And you get the answer that we got. So you see how they've quietly written the left-hand side as delta V? That delta V, though, is the potential difference of where you want to find it versus your reference. That's what this is hiding under it. But they've quietly written it as delta V. Okay? So again, you can see it here. That's the form. And you can't get rid of this guy. Sad face. Okay? So I wanted to show you this because the potential is where it's at with these problems. I think you can do the Gauss's law part, but the potential is like where it gets difficult. So let's keep moving and do another one here. You can tell what the Gaussian surface is going to be. But again, how did I determine that? How did I know that? Well, as these are shooting electric field toward each other, you might think that these lines can curve around and go this way. But when they go that way, they're eventually going to encounter another charge here that's going to block them. So the only choice they have, right, as these go toward each other, is to actually come in and out of the page right now. That's literally all they can do. Again, even those that curve around here, again, they eventually meet another charge over here, right, that emits electric field. They can't escape along the plane's direction. So what I'm saying is the electric field of an infinite plane, immediately you expect it to be either pointing up. Let's make smaller vectors, either pointing up or pointing down if you're below it. That's the kind of direction you expect, right? So if this is the Z direction, okay, the electric field is having some kind of Z direction itself. And now you go, okay, if I have 2 points here, P1 and P2, right? Do they see anything different? Well, not really. Again, because the plane, it's the same argument as before. The plane extends infinitely for them both. They see the same picture. It's like scrolling an endless film in front of you. You see the same film underneath you. If this endless film comes into your perspective and leaves your perspective, your horizon, it's always the same thing that you see. So P1 and P2, again, don't see a difference. But who would see a difference? You'd think that P3 would, right? You'd think that P3 would. But here's the catch, okay? All three of these points actually see the same picture. Now, P3 is a little more complicated to explain, but I'll explain it like this. How can P3 and P2 experience the same electric field? How's that possible? Let me explain with a little bit of an aside here. to convince you. If you're close to the plane right now, here's what's happening from the plane to you. You get contributions right now, very strong contributions from these close-up charges, okay? And you can see what the symmetry here does, by the way. It doesn't take a genius to see that the electric field, again, at point P3 will, like, the only component that will remain is going to be in the Z direction. It doesn't take a genius to see that, you know, this, again, and that have components in the planar direction that cancel, right? And you only have, like, you know, this. And again, same for the reds. You can see how they go. And you only have, again, this part. Actually, these should be larger vectors. Excuse me one sec. Let me make them realistic. The red vectors should be a lot larger than the yellow vectors because the charges are closer to point P3. Just doing it logically. Like that. So again, you can see what's going on. I'm going to get to point P2 in a second. Let me show you something. Okay, so overall, we can tell, right, what direction the electric field is going to be from this diagram as well. We can tell that the electric field is going to be in the Z. Again, you can see it. But what about, again, what I was telling you, how do I convince you that there is no dependency in the Z itself, that the electric field is going to be a constant? How do I convince you about that one? That one is a little more challenging to show, but I will try it. So take a look over here. I don't know how much Brenda has explained about this, but take a look at this. If I go further right now, let's say this is my point P2. Okay? What's happened? Well, let me explain. So the ones that were, these two guys that were close to you right now, they're much further away from you. So they contribute when they hit you right now, okay, when they hit you, they contribute much smaller of an electric field. I'm going to try and aim it correctly. They contribute a lot less of an electric field than they did on point P3. So I'm trying to aim it correctly. I'm going to do the P3 point there like that. So the electric field lines, again, just being at point P3 like that. Perfect. But then the thing is, do you notice that even though they're a lot smaller, I'm going to make them again to scale. They should be, let's say, this big right now. Right? Like, they're not that much smaller than these because I didn't move P2 very far away, right? It's still like here right now, roughly around here. So these are the same field lines that are coming from these two guys. I need to specify where they're coming from just so you're not confused. And these come from these two guys. The orange ones come from these two guys, the edges here. What do you notice though? Take a look at the magic that's happening here, okay? I hope I hit this correctly. But what do you notice here? Take a look at the symmetry this time. The planar components, yeah, they still cancel just like they did before over there, right? They still cancel, but what has remained here, I hope I hit it correctly. I did it by eye, is the same as it was here. Whoa. So because the angle became narrower, look at this angle here, was so wide before. It was such a big angle right now. It has become narrower now. And because it became narrower, even though the electric field dropped in strength, the effect of you moving away, it narrowed this angle and maintained the component here to be the same as it was here before. Isn't that crazy?
I have a question.
Yeah, Grace.
So why does the distance not matter here, but with the infinitely long line of charge, the distance did matter?
We didn't have this kind. Well, okay, in the infinite line, it's a different sort of situation, right? So in the infinite line,
when you move further away right now, you don't have, you don't have the same kind of charge distribution that causes this. Let me explain. So we do have again, the narrowing of the angle here as well, when we compare 2 points that are far from each other, like P1 and P2. We do have the narrowing of the angles again. Yes, from the individual charges, okay? They become narrower, like that. The problem, though, is that in the plane situation, okay, we always find charges. So this guy is an infinite line. And I wish I had good demos here around me to show you this better, but it's an infinite line. It doesn't have extent in this direction at all, okay? Our plane has extent in this direction. So me being the charge right now, I'm underneath the plane. I'm underneath the plane right now like this, okay? When I look above, I see a ceiling of charges, right? And it's an endless ceiling, right? It goes this way, it goes backwards, left, right? And I'm just sitting underneath it and looking. And when I move myself further, like if I lower my height right now and move away from this plane, my horizon, Grace, increases. So even though I'm further than the middle charges over here in this area, now the charges that I couldn't see in my horizon, they come in my horizon. Okay, they come, I can see them now. And if I see them, I can interact with them. So where these guys are losing the game in terms of strength on me, I am adding contributions from the people in the horizon that I couldn't see before as I'm moving away. So again, if I do it in a side view, you have the plane here, you have the charge here, right? Let's say its horizon, again, if it's here, its horizon is like the edge of the folder here. So let's put it right beside. But when I move backwards, you see now this charge.
Wait, are you like drawing on the board or something? Because I can't.
No, I'm on the camera. I'm on the camera.
Oh, okay.
So when we're right beside, our horizon could be just a folder here, okay? But when we move away, we get to see parts that we couldn't before, above and below the plane and on the sides. So when we move away, the middle part loses strength on us, but that loss is made by the new charges that we get to see now from our new horizon. They push us forward.
Okay, so to clarify, like, does the potential, right?
The potential, we will find it. Do not worry about that. But
either way, like, so it's the same despite the distance from the plane, and it's the same despite the distance from the line, like the force of the electric field on it.
not the potential is not constant, because there is electric field around the plane, and when there is electric field, potential changes. We've talked about this.
We were talking about like finding the strength of the electric field, right?
Yes, and I'm claiming.
Yeah, so the strength of the electric field is the same in both scenarios, like for both the plane and the line.
No. So
No?
the line doesn't have, so the horizon of the line, again, it doesn't actually provide you with our independence. Okay. The plane though does, and I need some very sophisticated diagrams to show you the actual like points in space, but I did it naively here just by hand and showing you that on the plane, basically, it's because of this angle narrowing down that you get the same kind of contribution from the charges, even though you're moving far away from them. Now, that's not the only effect that you have here. You have one more effect on top of this, which is, again, I told you, the introduction of charges here that you didn't see before. When you were too close, you weren't able to interact with those charges that are near infinity here. They barely saw you, and they didn't contribute at all toward your theta direction. Like if there was a charge right now here, look how tangential the electric field is that it causes at P3, and it's also tiny.
Look how small and tangential that electric field would be. It would almost contribute nothing to the Z direction right now. But when you're here, the infinite charge that was here right now, right? The infinite charge, it's still small, the contribution that it has at point P2, but it's more tilted now toward the Z. You have a Z component now that's considerable versus here. So what I'm telling you is the side charges here toward infinity get to see you better when you're further away, and they make up for the loss of the strength of the electric field from the middle charges. That's what's happening. It's like a trade of power. The middle charges are losing their influence on you, but the outside charges are building up their influence on you. So it's kind of an equilibrium. As the middle charges lose their influence on you, the side ones pick up. That's why the electric field actually is not dependent on any variable. It's a constant if you've ever derived this. Knowing this, again, you could have guessed that it's Z dependent right now. Maybe, I might have, okay? But it wouldn't matter. You'd still get the same answer, surprise. So I'm gonna guess here, okay? Knowing these things, that the electric field is a constant and it's in the Z direction. So if it's constant and it's in the Z direction, what kind of shape could I use? Well, I go, it needs to have one of its sides parallel to this. The only thing that can have one side, again, have a normal parallel to Z is a box. That's the only closed surface that I can have that can do that. That's why you see me have a box here, right? That's what's going on. And
Why can't we
again,
use cylinder? Oh,
you
just
can
because
use
like
a cylinder.
it wouldn't
It's
fit
the
well with
same.
the square dimensions.
yes, you can use a
Okay.
cylinder. As long as it has a flat surface along the Z, it will work.
Okay.
Okay. So what I do here, Olivia, is take a look. I'm going to stretch it. I'm going to test you. I'm going to stretch it like this. Now, George said, okay, there's electric field above and below. Okay. And it looks like this. Do you see which sides are actually going to be receiving right now flux?
Yeah, everything. Yeah, sorry, just the top and the bottom, and not any of the side pieces.
Exactly. So if we called right now these sides again, 1 and maybe 2, these are the only ones that are going to get flux. So as I go right now and do my closed surface integral here for the electric field, I know that I can open it up, okay, into 6 pieces. Like I can do this, I can do the second one. Don't forget your vector signs, right? All the way to number 6. I can open this up on its 6 sides. I hope you understand what I'm doing. I'm just opening up the surface on its 6 sides. And everybody beyond here is 0. But these guys are not. You can see them, how they're getting flux right now. And we're claiming that they're going to get also a uniform electric field through them. Like the strength is going to be uniform. When you're investigating these surfaces, you're going to get the same strength. Any point on them is going to get the same strength. Okay. So they satisfy right now. They satisfy the simplifications so that I can pull outside the electric field like that. And then I notice what's happening here. Wait a minute. These are the areas of these planes. And I can give my Gaussian pillbox here, whatever the heck dimension I want. I can call this X. I think this was Z, what we called this one here. I can call this Z, X, and Y over here. So what is the area dA1 right now? Grace. What is this?
Y times X.
What do you think this is?
Also Y times X.
Yeah, so in total, In total, you get 2EXY. Okay. What about on the other side, though? What's going on over there? Well, there you got Q enclosed over epsilon naught. And you go, okay. What is Q enclosed over epsilon naught? Let me get Kelly on this real quick. Kelly, you enclose this business over here. This is a 2D shape right now. The charge is in here that you're enclosing. It's defined by a sigma. And I want you to tell me what you believe I should do with this sigma to get the charge enclosed right now in here in this. Again, I'm gonna get rid of this stuff. I just want the charge inside.
Sigma times the area.
Yeah. And what do you think the area is actually gonna be? By the looks of it, what do you think it's gonna be?
X and Y too.
Yeah. Okay. So we got sigma, she's saying, times that area over epsilon naught, very correctly. Then I go in the next step and I go, and she goes, yeah, that area is just XY right now. So sigma XY over epsilon naught. And then we get sigma XY over epsilon naught here too. Obviously, it doesn't matter, like I said, how big you make that plane. So they drop. And what do you notice? I get E is a constant. And this is the constant itself. Now, this is a piecewise function. It's plus Z for values of Z above our plane. It's negative Z hat for values of Z below our plane. That's how I would present it. And that's that. Before you go, okay? Before you go, how do I get the potential for the plane right now before you go? Well, it's an infinite distribution. George said probably won't work if you take infinity as a reference. Use a reference point other than infinity. So I'm going to go ahead and show you again how to do that. Delete some information, save some space. Okay. So I'm going to pick here a point that is on our side one. That's going to be the point that we want to find the potential at. So we're going to give it some Z right now. We're going to give it here some Z. Shouldn't be taking more than 5 minutes to do this. Okay, so that's Z. And then we're going to pick some reference point, maybe here, where I'm going to give this guy some Z naught. Let me delete that stuff. So this guy here again above the plane is going to be sitting at some value Z naught. Here we go again. V at P minus V at P naught, that's our reference to P naught, is equal to the integral from P naught to P E dot DL. Okay, so I go in, all right, BP, I'll move, I'll understand that P here stands at the value Z. I'll move this on the other side. And P naught again is at a value of Z equal to Z naught. And then again, I go and investigate the electric field. George found sigma over 2 epsilon naught Z hat. You're in Cartesians. If you do this dot product in Cartesians, you're going to just get dz. So your integral should be varying with Z. Yes. And where are you integrating? Between your reference and your point of interest. Okay, not that bad. So you keep on going. You see again that you have a constant in the integral. You can pull it outside and just have dz remaining in your integral. So this here goes from Z naught to Z. Good. Maybe this will give you a surprise as compared to the previous problem. Let's see what happens. The integral of dz, I mean, come on now, just Z. And you're evaluating the balance here from Z naught to Z. So this leaves you with, right now, if you do it, with a very simple expression. we can add here this, and it would be Z naught minus Z. Now this is relative, because if you were doing the below part, that negative would have been a positive. So it's relative on which side you're on of the plane, but this is the form, okay? And you go, hold on a sec. Can I use Z naught equal to, can I go to infinity right now? Like, you know how we used to take for the sphere infinity as the reference? Can I go to infinity? Well, what would this end up being if you went to infinity? Olivia? Is it cool if I choose infinity as a reference?
I'm not really sure. I mean, like the way it would affect it up top is, wouldn't it still be infinity?
Yeah, that's bad. What kind of reference is this? But okay, I'll ask all five of you. What do you think is a good reference? Right now, we can actually choose something clever. We can see what we should use.
Can you show the diagram and everything again?
So Z naught is the distance again from the plane in the Z direction, right? Up and down here. And
Okay.
you don't need the diagram here, Olivia. You just need a place for Z naught to not ruin the actual potential function, to not diverge it. What's a good one that we wanted to use previously, but we couldn't? Wouldn't it be nice to not have this here? I'm just saying. What do you think?
Zero.
Zero?
Yes. Okay. So if we choose 0, then, you know, we just get Z back. That is wonderful, right? That actually is cool. So that means we can go and write this as this. In this case, it would have been negative sigma Z over 2 epsilon naught, like that. But if you approached it from below, right? If you did the potential, this is like for Z greater than 0, I suppose. Okay. For Z less than 0, the electric field flips direction. That's what I want to warn you here. So it's exactly the same crap over here. You don't have to rewrite it if you realize it, but it's the exact same crap. However, Z would actually be negative Z hat, right? Because the electric field is opposite. So that would get you plus here, right? As you're doing this, and then you would get this, right? So, you know what I mean? It's not that different. It's exactly the same, just a plus. Now, okay, to combine both of these results, okay, to combine both of these results, before I make the simplification over here, to combine the results that I got here, I can be more clever than this, girls. Come on. Come on now. This is working for Z greater than 0. This is working for Z less than 0. What if I just combine the results for both cases and I said my potential in the Z is this reference potential plus the sigma over 2 epsilon naught, but then I just subtracted the absolute value of Z. That could also work, okay? Let me make sure I'm doing this right, of course. 1 second. So there's the negative there from Z naught to Z. Okay. Yeah, we're good. So I can combine these. I can combine these with an absolute value and express both above and below the results in one function and just get over it, you know? But even if you don't do this, if you don't see this during an exam or whatever, just do this, okay? just ask yourself, can I use these? The left one here, the 0 worked. Obviously for the right one, the same stuff will work too. So if I do the right one, I'm just going to get here plus Z instead of negative Z. That's the only difference, and everything else is the same. So what do we conclude then? We conclude that our potential function, when we combine all our results together, will be V of Z, some constant potential. We said that we're going to take 0 now as Z naught, and we add to it sigma over 2 epsilon naught. And since Z naught is 0, it vanishes. So we got, here's how we need to be careful about this. I should write this as like this, right? For Z, again, greater than 0, for Z less than 0. All right. Perfect. And then we are in, yeah, that's all. So this summarizes both cases, above and below the plane. And again, you have the choice, okay, to set that potential to 0. The reference potential. That's up to you, okay? So it is a function of Z, as you expect, okay? It is a linear function. And to prove, before you go, again, electric potential infinite plane. Maybe the physics stack exchange then. So yeah, they try to combine here both of the, this is for a finite line, what they're finding here right now. Where is the infinite one? Not here. Great. Electric potential of a charged plane's sheet. Is this finite? Yeah, you can kind of see here. It's not what I want. I don't know. Sometimes it's hard to find exactly what you're looking for here. Electric potential infinite plane of charge. Okay, let's try this one. I think they're going to give it to them. So V is a function of Z, yes, and they never solve it. So yeah, that's the sad thing with physics forms. Sometimes they never solve the question. They just give the hints, and they're like, bye, see y'all later. But there it is. Suppose we have a uniformly charged sheet, right? Therefore, calculating the electric potential, we'll have something like this for Z greater than 0, and this for Z less than 0, and we take the limits. Yeah. So you see again, they've ignored the Z naught. They've set it equal to 0, and they've set the V of 0 equal to 0 when they use this result. You can do that. I said it's a choice. Okay, so now you understand that even though the electric field is constant, that doesn't mean the potential doesn't change, because as I'm coming in, right, I am going against this. I am gaining potential, right? This is making me gain potential. Remember, electric field points to where the potential decreases, okay? And that's what I have for you for tonight, I guess. I don't want to go overboard. We're going to do a lot more geometries in the next session, okay? In the next session, I'll pick and choose here. Definitely want to see you do conductors here, 100%. And maybe this guy. So yeah, I'll try for Monday. Let's agree on a time. And I'll stop, I guess, if I was recording, I'll stop it here.